When the Wright brothers began their path toward the invention of the airplane in 1899, propulsion was the least of their worries. They were focusing on control, aerodynamics, structures, and because there had been a progress on lightweight steam and internal combustion gasoline engines in their day, they thought it would be an easy matter to marry one of these lightweight engines with their airplane design. Same thing with propellers. They thought after decades of experience of propellers used on ships, it would be a simple matter to adapt that to the airplane. Well, they were actually quite wrong about that. The engine that they needed really had some very specific requirements. It had to be much lighter than most of the internal combustion gasoline engines of their day. But it didn't need to be very sophisticated because the Wright brothers had so successfully designed their airplane that they just needed a very low horsepower engine to get their airplane in the air. And they designed an engine which was very simple, had no carburetor, no fuel pump, very simple design, and it generated 12 horsepower, 4 more than their basic design estimate required. So they thought they would be okay. Turns out their airplane was much heavier than their design estimate, so that extra 4 horsepower really came in handy when they attempted to fly the airplane. The other component of their propulsion system, the propeller, was even more significant because the Wrights really were the first to conceive of an aerodynamic propeller, as opposed to a ship propeller, which simply pushes the ship along. An aeronautical propeller is really a wing moving in rotary motion, and it generates a horizontal force we call thrust. Marrying that propeller with their simple internal combustion engine, they created a propulsion system. And it's important to think about it as a propulsion system because the Wrights understood that an airplane was many dimensions. It was a wing, it was a structural design, it was a control system, and a pilot. And the propulsion system was one component of that. All of these things had to work together. An airplane was not just one invention, it was many inventions, all of which had to work in concert.
Let's take these concepts of lift and drag and apply them to propulsion, which is another of the 4 central forces acting on an aircraft in flight. The entire idea behind propulsion systems is to produce the force needed to move the aircraft through the air, overcoming aerodynamic drag in the process. In modern aviation, there are 2 main types of propulsion systems in use: propeller-driven airplanes, powered by an internal combustion engine, and jet-driven aircraft, powered by turbojet engines, or the often even bigger turbofan engines. We'll focus on propeller aircraft in this lecture and turn our attention to jet engines in the next lecture. So, why have these 2 types of engines emerged to the forefront of aviation instead of other propulsion devices? For example, steam engines were sometimes used in the early days of aviation, but are hardly ever seen today. Or rocket propulsion has been used for some aircraft, such as the Bell X-1, that first broke the sound barrier. It turns out that one of the most important features of a propulsion system is the power-to-weight ratio. We can think of this as a metric for efficiency of the engine. We want to get as much power as possible out of the system while minimizing the weight. This was one of the most critical limiting factors in the early days of aviation. Propulsion systems were available that could produce substantial power, but they were very large and heavy systems, making them impractical for use on aircraft. Even the Wright brothers' engine had a fairly poor power-to-weight ratio of 1 horsepower per 16 pounds. Following their work, engine performance rapidly improved to values much closer to 1 pound per horsepower. This power-to-weight ratio continues to be a driving design criterion for aircraft designs created today. What makes jet engines and internal combustion engines so popular is that they operate off of fossil fuels, which have an incredibly high energy density relative to other forms of energy storage. This feature comes back to the problem of weight on an aircraft. The air vehicle must carry around the energy source, that is the fuel, along with the energy conversion device, that is the engine. Other energy storage methods and energy conversion methods are available, such as solar cells, fuel cells, batteries, chemical rockets, and even nuclear propulsion. However, none of these methods can currently match the efficiency and lightweight of using fossil fuels in an internal combustion engine. So in this lecture, we'll focus on how internal combustion engines operate to produce power, and how the propeller transmits that power to the air. Let's start with the discussion of the internal combustion engine. The central function of an internal combustion engine is to convert the chemical energy stored in the fuel to mechanical energy in the form of rotating shaft. The substantial amount of energy stored in fossil fuels is released by burning the fuel in the combustion event. That energy is then used to push a piston sliding within a cylinder, which then rotates the crankshaft. Aircraft engines will have a number of cylinders arranged such that each piston is connected to the crankshaft, and the power output from each cylinder is contributing to the rotation of the shaft. The firing of the cylinders is timed such that the combustion events are spread evenly throughout the complete rotation of the shaft. The arrangement of the cylinders can be in an inline array around the perimeter of the engine called the radial configuration, all in a line for the inline configuration, or in a V configuration with 2 rows of cylinders arranged in a V shape. Let's take a closer look by examining this schematic of a 4-stroke engine. The 4-stroke engine is so named because there are 4 key segments of the entire cycle of its operation. The first stroke of the piston within the cylinder is the intake stroke. During the intake stroke, valves on one end of the cylinder open in order to allow a mixture of fuel and air into the cylinder. The next stroke is the compression stroke, where the piston compresses the fuel-air mixture within the cylinder by decreasing the volume. During the compression stroke, the pressure of the fuel-air mixture increases dramatically. At the conclusion of the compression stroke, the volume of the fuel-air mixture within the cylinder is at a maximum, and the pressure is at a maximum, and the spark plug is fired. With the firing of the spark plug, the volatile fuel-air mixture ignites and rapidly releases the energy through this combustion event. That combustion process rapidly and substantially increases the pressure of the contents within the cylinder. This higher pressure then applies a very strong force on the face of the piston, pushing it back down through the cylinder. From the point of spark plug ignition, the third stroke of the piston initiates. This portion of the cycle is called the power stroke, which is when all of the energy from the combustion event is used to force the piston downward, increasing the volume of the mixture. The energy from the combustion event is transmitted to rotation of the crankshaft by the piston and its connecting rods. Following the conclusion of the power stroke, the fourth and final stroke initiates when the cylinder is at the bottom of its stroke. A second set of valves opens, allowing the byproducts of the combustion event to be exhausted from the cylinder. The piston moves upward, pushing the combustion products out of the cylinder through the exhaust manifold. So, in summary, a 4-stroke engine is composed of the intake stroke, the compression stroke, the power stroke, and the exhaust stroke. Let's take a deeper look at the function of the internal combustion engine by considering a plot of the pressure versus the volume of the contents within the cylinder. We call this a PV diagram. If we plot points on this diagram corresponding to each stroke of a 4-stroke engine, we can see how the pressure and volume varies throughout the cycle of the engine. From that, we will be able to see how much work the engine is producing and what we might be able to do to improve the performance of an engine. If we begin with the start of the intake stroke, we'll note that as point 1 on the PV diagram. As the piston moves, the pressure within the cylinder remains approximately constant because the intake valve is open. However, the volume of the contents increases substantially due to the movement of the piston. Let's mark the conclusion of the intake stroke as point 2. Now, moving into the compression stroke, the volume again decreases due to the upward movement of the piston, and the pressure increases at the same time. This is because all of the valves on the cylinder head are closed, and the contents of the cylinder are compressed. The conclusion of the compression stroke is noted as point 3. The power stroke will be represented by 2 segments. The first is the combustion event, represented between points 3 and 4 on the PV diagram. Here, the spark plug is ignited, and the contents of the cylinder are rapidly burned. This combustion process, of course, takes place within a very small fraction of the overall period of the cycle. the pressure within the cylinder dramatically increases due to the release of chemical energy in the combustion event. The power stroke then continues, moving from point 4 to point 5, where the volume of the cylinder is increased as the high pressure pushes the piston downwards. At the conclusion of the power stroke, the exhaust valves are opened, which quickly relieves the pressure within the cylinder, so the pressure drops from point 5 to point 6. This marks the beginning of the exhaust stroke, which continues from point 6 back to our initial condition of point 1. Between point 6 and point 1, the volume of the cylinder decreases and the pressure remains constant as the piston pushes the exhaust gases out of the cylinder to refresh the conditions for the next combustion event. Now, this PV diagram can tell us some important things about how the engine performs. Power is defined as work per unit time, and mechanical work is equal to the force times the distance that the object is moved. So to maximize power output, we need to maximize the force applied to the piston and the distance that the piston moves, while doing that within a minimal amount of time. Here, the force acting on the piston head is related to the area of the piston face, the cylindrical cross-sectional area, and the pressure acting on the piston, since pressure is force per unit area. So higher force will result from higher pressure acting on the fixed surface area of the piston face. The distance that the piston moves is called the stroke. Larger stroke results in larger displacement and more work done. Stroke is also related to the displacement of the cylinder, which is basically the volume of the cylinder swept by the movement of the piston head. Keeping these ideas in mind, we see that we want to increase the pressure excursion between maximum and minimum pressure acting on the cylinder, and we want to increase the volume swept by the piston in order to maximize power. Based on these thermodynamic principles, it turns out that the amount of work done by the gases inside the cylinder on the piston is equivalent to the area encompassed by the cycle from points 1 through 6. Before the ignition event, during the compression stroke, the pressure and temperature increase because the movement of the piston is adding energy to the air, because it's doing work. And following the ignition, the air in the cylinder does a lot of work on the piston, with a net positive work output. Let's take a look at how the temperature of the air in the piston changes throughout the cycle through a demonstration. I have a small cylinder with a piston that I'm going to use to compress the air inside. I also put a bit of tissue paper inside, which will help us visualize what is happening to the air temperature. My goal is to burn the paper. But let's see if the temperature will get hot enough. How hot does it need to be? Well, if you've ever read Ray Bradbury's Fahrenheit 451 novel, you'll probably recall that the combustion temperature of paper is 451 degrees Fahrenheit. Let's see if we can get that hot. Wow, very nice. So if we assume that all of the energy I put into the cylinder through work went into heating the air inside, then thermodynamics tells us that the temperature rose to over 1,000 degrees Fahrenheit. So the compression stroke is definitely adding energy to the air in preparation for ignition. Now let's consider the impact of pressure in a little more detail. The pressure that the engine can supply to the cylinder is directly related to the ambient air pressure. You'll recall from our second lecture that atmospheric pressure decreases as we go up in altitude. So naturally, the power that can be produced by an engine diminishes as an aircraft climbs to higher altitude. In the early days of aviation, this quickly became a limiting factor on the maximum altitude of an aircraft. At heights above about 18 or 20,000 feet, there simply wasn't enough air to support the combustion event, and the power dropped off substantially. Ultimately, this lack of power would prohibit any further climbing of the aircraft, and the altitude would max out. But that's not the end of the story. If there's a way to somehow boost the pressure of the air supplied to the intake manifold, then we can keep the power output of the engine at the sea level rated power output, even at higher altitudes. This is exactly what can be done with a supercharger or a turbocharger. These two devices essentially perform in the same way. Each boosts the pressure and density of air delivered to the intake valve with a compressor. We're at the Aviation Institute of Maintenance in Manassas, Virginia, where we're going to talk about the turbocharger and the supercharger. The function of these is to deliver high-pressure air to the intake manifold to be able to fly an aircraft at high altitudes, because we have to have enough air for the combustion event. The turbocharger actually operates off of the waste energy in the engine exhaust. That exhaust gases comes through and is passed through this turbine right here. As it passes through the turbine, it's pulling energy out of that exhaust and driving a shaft connected to the compressor here. The compressor turns and sucks in air through the inlet here and is a radial compressor and sends it back out to this radial exit here to deliver high pressure air to the intake manifold. Compare that with the supercharger, which instead of driving off the exhaust gas has a shaft here connected to the main drive of the engine to drive the compressor, but then otherwise the function is the same. It pressurizes the air through this radial compressor to deliver that high pressure air to the intake manifold. So let's consider the implications of what we found. Higher displacement or volume of the cylinder will result in higher power output. Also, the more cylinders we have working together, the higher the power will be. And the faster the cylinders fire, the more work is done per unit time, so the power output of the engine goes up. Finally, higher pressure allows more fuel to be burned and will give higher power output. These factors are reflected in the progression of engine technology that we've seen in engine development. The Wright Flyer's engine had 4 cylinders with 201 cubic inches of total displacement. The engine produced about 12 horsepower with a weight of 200 pounds, giving it a power loading of about 16 pounds per horsepower. Compare this with the stats of the Rolls-Royce Merlin, a liquid-cooled V12 which was used on the P-51 in World War II. This engine had 12 cylinders, each with 137 cubic inches of displacement. This packed much more punch, giving 1,580 horsepower while weighing in at 1,640 pounds. The power loading of the Merlin was 1.04 pounds per horsepower, much better than that of the Wright's engine. One of the major drivers of engine technology that we haven't yet addressed is the vexing problem of how to cool the engines. The combustion events produce a significant amount of heat, which is directly transferred from the combustion gases to the cylinder walls. This heat must be effectively removed from the engine in order to prevent warping of the cylinder head and ultimate destruction of the engine. 2 key cooling technologies are convective cooling via airflow over the cylinders or liquid cooling via circulation of coolant around the cylinder heads. Each of these techniques can substantially increase the weight of the engine, and so engine cooling was a key area of technology development that improved engine performance in the early days of aviation. The engine that the Wright brothers used on their 1903 Flyer employed evaporative cooling of a fluid. It turned out that this technique wasn't very efficient and only enabled operation of the engine for a period of several minutes before the engine overheated. Engine designs in the earliest days of aviation then quickly pivoted to air cooling, which involves direct airflow over fins mounted on the cylinders. In order to maximize the flow of air over the cylinders, the radial engine was invented, where each cylinder was equally exposed to the oncoming flow. However, air-cooled engines had the limitation of limited cooling when the aircraft was on the ground or in low-speed flight. This frustration led to the ingenious development of the rotary engine, which rotates the entire engine around the crankshaft. This afforded the advantage of continuous movement of the cylinders relative to the surrounding air, resulting in air cooling even when the aircraft was stationary on the ground. Ultimately, however, the rotary engine suffers from mechanical problems associated with rotating the entire engine assembly due to the very high inertia associated with rotating a heavy engine. The size and ultimately total power output of the engine was limited. Furthermore, there were challenges associated with effective lubrication and reliability. Thus, the rotary engine quickly fell out of vogue near the end of World War I. Despite these challenges of air cooling, radial air-cooled engines continued to be used throughout the interwar era. The 200 horsepower Wright J5 Whirlwind engine was used by Charles Lindbergh on the Spirit of St. Louis and won the Collier Trophy in 1927 for its advancements to the state-of-the-art in engine technology. Also, due to the robust nature of air-cooled designs, with fewer moving parts, the engines tended to have robust performance. For this reason, the US Navy used many air-cooled designs throughout the interwar era and into World War II. Liquid cooling is the other major method for removing waste heat from the combustion process. The huge advantage of liquid-cooled engines is that airflow over the engine block is not required for cooling. This allows for effective cooling no matter what the speed regime is. Sudden changes in power level and accompanying thermal stresses due to changes in air cooling are not a significant problem. Furthermore, the cylinders can more easily be arranged in line without worrying about maintaining undisturbed airflow over subsequent cylinders. A long arrangement of inline cylinders produces a much more slender engine block, which allows the aircraft fuselage to be more streamlined with less drag. For this reason, liquid-cooled engines were very popular with military aircraft designers, where speed was of paramount importance. A good example of this type of engine is the Rolls-Royce R, a V12 supercharged liquid-cooled engine with 2,239 cubic inch displacement and 2,350 horsepower at 3,200 RPM. With a weight of 1,640 pounds, it had a power loading of 0.65 pounds per horsepower. This beauty of an engine was tightly integrated into the Supermarine S6B, which was flown at 340 miles per hour to claim the 1931 Schneider Trophy for the fastest seaplane. Now, as we wrap up our discussion of internal combustion engines, let's touch on the topic of how the spark plugs are fired. Unlike car engines, which distribute power to the spark plugs via the car's electrical system, an aircraft can operate with absolutely no electrical power on board. This is done through the use of ignition magnetos, which generate pulses of high voltage by the rotation of permanent magnets. The magnetos will produce electrical pulses needed to fire the spark plugs as long as the engine is rotating. Since redundancy is so important on an aircraft, nearly every engine has 2 spark plugs for each cylinder, as well as dual magneto systems. If one spark plug gets fouled, or if one magneto set fails, the other should keep on operating and producing enough power to make it safely to an airport. For aircraft such as older versions of the Piper Cub that have no electrical power on board, the propeller must be initially rotated through some means in order to get the engine started. This can be done with a pilot in the cockpit, holding the brakes tightly, and a buddy who hand rotates the propeller and quickly ducks out of the way as the engine fires up. For those aircraft that do have an electrical system, the engine can be started via an onboard battery and starter. However, the magneto ignition system is still used, since it adds a level of robustness and safety. The magneto ignition system allows the engine operation to be entirely self-contained and independent of the aircraft's electrical system. I speak from personal experience, having found that this level of redundancy is extremely helpful. One time on a night flight, I experienced an electrical system failure in flight. The alternator failed, and the battery completely drained over time. Despite this, it was very comforting to know that the engine would keep on humming along without missing a beat, even without the electrical system being present. I just had to find my way home in the dark. Let's now turn our attention to the propeller. Once we've generated all of this horsepower at the shaft of the engine, the propeller is what transmits that power to the flow to actually pull or push the aircraft forward. We can think of the propeller as simply a rotating wing, composed of a series of airfoils that produce lift. Since the airfoils are rotating about the longitudinal axis of the aircraft, the net lift force produced by the propeller results in thrust that is oriented in the direction of flight. It may seem like a simple concept, but there is some nuance to how a propeller is designed and operated. We'll consider 2 key ideas about propellers. First, if you've ever looked at a propeller up close before, you've noticed the twist of the blade from the root to the tip. Here's the twist of the blade from the root to the tip. Second, it turns out that the efficiency of the propeller depends significantly on the forward flight speed and the rotational speed of the propeller. Even though there are efficiency problems at off-optimal conditions, there is a way of working around that. So let's dive in. Now, it's important to set the correct vantage point for thinking about propellers. Even though they are sometimes referred to as air screws, it's not accurate to think of a propeller as screwing through the air. as though the air were a solid mass. Instead, it's best to think of the propeller as a rotating wing. It is this rotating wing that produces the lift that accumulates into an overall thrust vector that propels the aircraft forward and overcomes aerodynamic drag. We'll need to take a look at the propeller performance by considering individual cross-sections of the blade. Each cross-section is an individual airfoil. However, the velocity seen by the airfoil has some significant differences from what is seen by the wing. Since the propeller is rotating, the net velocity at the airfoil section is a combination of the aircraft's velocity with the tangential speed of the propeller at that spanwise location. This tangential speed is the angular speed times the local radius. For locations on the propeller blade that are very close to the hub, the tangential speed is very low since the radius is small. However, at the propeller tip, the tangential speed is at its highest since the radius is at the maximum extent. It turns out that this spanwise variation in tangential speed has a significant impact on the propeller's design. The best way to understand this is to visualize the local velocity seen by a particular airfoil section along the propeller span through the use of velocity triangles. Let's consider two spanwise locations, one near the propeller hub and one near the propeller tip. At each location, the aircraft's flight speed is the same, which we'll indicate as v infinity. The tangential speed at the hub is very low, since the radius there is small. When we add these two velocity vectors together in a head-to-tail fashion, we can draw the hypotenuse of the triangle to indicate the net velocity experienced by the propeller airfoil section at that location. At the hub, since the tangential velocity is so low, the angle of the net velocity vector is very high with respect to the plane of the propeller's rotation. At the prop tip, however, the tangential velocity is very high, making the angle much shallower with respect to the propeller plane. Now, if the propeller's airfoil sections all had the same pitch angle, the angle of attack of the flow at the propeller hub would be very low. In fact, the angle here would likely be so low that it would be negative, producing extra drag instead of thrust. At the blade tip, on the other hand, the angle would be so high that the local flow would be separated and the tip would be stalled. Thus, the blade must be twisted in order to optimize the airfoil pitch angle relative to the local angle of attack. At the blade root, where the angle with respect to the prop plane is so high, the blade must be pitched to a very high angle in order to get a reasonable angle of attack. As the location along the span is increased, the flow angle decreases and the blade pitch angle must be reduced in order to maintain the same appropriate angle of attack. Thus, the blade pitch angle changes along the span from very high pitch angle to a very shallow pitch. This is due to local variations in flow angle. This twist of the blade is characteristic of every propeller on an aircraft. Let's now talk about the efficiency of the propeller. We can define efficiency as the ratio of the power supplied to the flow divided by the shaft power produced by the engine. It's an indicator of how well the propeller does its job of transmitting the engine power to the flow. For a well-designed propeller operating near optimum conditions, the efficiency can be near 85%. It turns out that there is an optimum flight condition where the efficiency of the propeller is optimized. In order to effectively describe this optimum condition, we need to introduce a non-dimensional parameter that is a ratio of how far the propeller moves forward divided by how far the propeller rotates around its radius. This parameter, termed the advance ratio, is determined as a ratio of the aircraft flight speed divided by the product of the rotational speed and the diameter of the propeller. At low advance ratios, the flight speed of the aircraft is very low relative to the prop rotational speed, while at high advance ratios, the flight speed is high relative to the rotational speed. We can now introduce the characteristic propeller efficiency curve for a propeller. This is a plot of propeller efficiency versus the advance ratio. When the advance ratio is 0, the forward flight speed is 0, so no thrust is produced and the efficiency is 0. Essentially, at low advance ratios, the flow over the propeller is predominantly stalled, so the efficiency is very low. As flight speed goes up, the angle of relative velocity vector goes down, the angle of attack decreases, and the flow angle approaches the optimum angle across the span of the blade. At the peak efficiency, we can say that a well-designed blade will have optimum angle of attack across the span of the blade, where the maximum amount of lift is being produced by each airfoil section. The prop efficiency must always be less than unity, since there will always be drag, even at the optimum condition. This drag takes the form of both parasitic drag and induced drag. Now, when we move to even higher advance ratio, the efficiency begins to decrease again from the optimum condition. This is because the flow angle is increased such that the angle of attack over some portions of the blade is negative and lift is lost. In fact, the local angle can become so low that drag is produced over some portions of the span instead of thrust. The overall efficiency drops off rapidly with increasing advance ratio until the point where efficiency drops to zero. At even higher advance ratios, the propeller actually acts as a windmill, producing net drag instead of thrust. So clearly, there is an optimum advance ratio that should be flown for a fixed pitch propeller. However, it's not easy to change the rotation speed of the propeller without changing the power output from the engine. Most propellers are directly mounted to the crankshaft without any gearing, due to the simplicity of this setup. So the power needs of the aircraft dictate the RPM, which dictates the advance ratio. If the aircraft operates over a wide velocity range, then the advance ratio will also vary across a wide range, and the propeller efficiency will be suboptimal over a wide range of the aircraft's operating conditions. Is there any way to decouple this? Yes. This idea is what led to the variable pitch propeller, which reached maturity in the 1930s. This development enabled much higher flight speeds by allowing the pitch of the propeller to be controlled to match optimum conditions throughout the flight envelope. An associated development is that of the constant speed propeller, which has a governor at the hub of the propeller to automatically adjust the blade pitch in order to maintain constant rotation speed. In this way, the engine and constant speed propeller work in concert with one another to maintain optimum operating conditions for the engine and propeller throughout the operating envelope of the aircraft. Okay, let's summarize. The basic idea is that engine and propeller work together to transmit power to the flow, which pulls the aircraft forward. The four-stroke cycle of the engine, intake, compression, power, and exhaust strokes, serve to effectively extract energy from the fuel and transmit that energy to the crankshaft. The crankshaft then turns a propeller, which has an optimum advance ratio, which is the ratio of flight speed to prop rotation speed. This optimum condition can be changed by using a variable pitch propeller or even automatically controlled by using a constant speed propeller. Now to wrap things up, have you ever wondered why propeller-driven aircraft are still out there flying today? With the advent of the jet engine, which we'll discuss in the next lecture, why haven't jets taken over completely as a dominant propulsion system for all types of aircraft? Simply put, the reason is that propeller-driven aircraft are more efficient than jets over the range of speeds at which they both can fly. However, propellers do not perform well at higher flight speeds. The drag rises dramatically as the local Mach number on the blades goes up. In fact, the local Mach number at the propeller tip can easily approach Mach 1, where shock waves would form and increase the drag substantially. This inefficiency of the propeller at high speeds, due to compressibility effects, which we'll discuss later, is precisely the motivating reason for the development of the jet engine. So in our next lecture, we'll take a close look at how jet engines achieve much better performance as we move to higher speeds.